Hi all, today we discuss section 3.6, the double dual. In the last class we have discussed what is a dual basis and how to obtain that basis from a dual basis from a basis of V. Now we have denoted that set as V star. This is set of four linear functionals, that is a function from V to F where F is linear. So this is the dual space linear transformation, and this is the dual space of V. If V is a vector space, is a vector space over F. If this is the case, then V star is the dual space for this V. And if we start with the basis of V, say alpha 1, alpha 2, etc., alpha n, then you can construct a basis for V star. Say V star. So this is a collection of all f1, f2, etc., fn. That means it consists of exactly n elements with the definition fi of alpha j, that is delta ij. So this is the definition of dual basis. In fact, this is LVF. In our earlier notations, we can consider this as LVF. Then or V star, then each basis of V, if this is a basis for V, then you can construct a basis for V star in such a way that Fi alpha j is equal to delta ij. Now we will consider the dual space for this V star itself. Okay, so what is dual space for V star? That means V star whole star. So this is defined to be the set of all linear functionals L from V star to the corresponding fields. Exactly in the same manner where we consider the V star, this is set of all linear transformations L from L is linear transformation, L is linear from V star to F. Okay. So in the same manner, if you start with the basis of V star, before that we consider this, we use this notation for V star, we consider V double star or double dual of V, double dual of V. Okay. So if we start with the basis of V star, say f1, f2, etc., etc., fn, then you can construct a basis for if we denote this as some V star, if this is the basis for this need not be a basis dual basis anyway. So this is the basis for V star, then you can construct a basis for I'll call it as B prime. This consists of elements L1, L2, etc., Ln with Li of Fj is equal to delta ij. Okay, so this is the dual basis for this V star. Okay, the dual basis or the basis of V star. Okay, now this means Lifj is a linear transformation. This is an element of V double star as well. So each Li is an element of this V double star. Okay. Now we define a linear map. Say each alpha belongs to V, and now onwards we will consider V. This is V. This is our V star, and this is our V double star. Okay. So if we choose an element alpha, we will define a unique element in V double star. Okay, say L alpha. Okay, what is L alpha? L alpha is a member of this one, V star, V double star. So L alpha should be a linear functional from V star to F. So each alpha belongs to V. We define a map L alpha, that is the map corresponding to alpha. This L alpha is a function from V star to F. This is the behavior of L alpha, and it is defined by L alpha of each element of V star. Here we define this is an element f alpha in F. So this is true for all F belongs to, this is true for all F belongs to V star. So this defines a linear functional from this this V star to F. Okay, so that is denoted by L alpha. So each element alpha the induces a linear functional from V star to F. That means each alpha belongs to V. There should exist an element, or we can define an element L alpha in this V double star. Okay, so first we have to verify that this L alpha is a linear functional from V star to F, okay, rather than a map. So we evaluate this L alpha times L alpha of C times F plus G. By definition, this is C F plus G of alpha, and this each F and G are this F and G are elements of V star. Then this can be written as, that means both are linear functions from V to F. Then this can be written as C times F of alpha plus G of alpha, and this F alpha can be replaced by L alpha of F. So this can be written as L alpha of F plus L alpha of G. Okay, this shows that this L alpha is a linear functional from the domain, the vector space which contains this CF plus D, that is nothing but V star. So this is a linear function from V star to F. Okay, so this defines a linear functional from V star to F. That means each alpha induces an element in V double star. So we can make a correspondence between this V and V star using this. Alpha is mapped to L alpha. So this is a connection between V and V double star, not V star, V and V double star, because this is an element of V double star and this is an element of V. Okay, now we will study more on this linear functional. Before all this discussion, when you define this L alpha, we can easily verify this correspondence. Alpha is mapped to L alpha. So this would enable us to define a map from a vector space V to the vector space V double star. Okay, so this is alpha here, and this alpha is mapped to L alpha here, and L alpha is defined to be L alpha of F is equal to F alpha. This is the definition of L alpha. Then we can verify this map. Okay, I'll write it as some psi from this V to V double star defined by psi of alpha equal to L alpha. This is the definition for all alpha belongs to V. Now we will show that this is in fact a map from this V to V double star. That means whenever this alpha is not equal to 0, we will prove that L alpha is non-zero. Okay, this shows that this will show that this map psi is a function from V to V double star. Okay, so how will you prove this alpha not equal to 0 implies L alpha not equal to 0? This is our claim. Whenever alpha not equal to 0, then you can consider a basis of V consisting of alpha, or extend. You can extend this non-zero element. Say I'll write the first element as alpha 1, which is alpha itself, and you can extend this to a basis for V. If V is n-dimensional, then there should contain exactly n elements. Then corresponding to this V, you can construct a dual basis V star consisting of the vectors f1, f2, etc. fn, and I'll call this f1 is defined as f1 of alpha 1 equal to 1. Okay, and f1 of any other element alpha 2, alpha 3, etc. are 0. Okay, and so on. So I'll write this f1 as f, the very first element as f, then f of alpha 1 is equal to 1, and rest of them are non zero quantities. So if this is the case, then how do you prove this L alpha is non-zero? If alpha is non-zero, there should exist f1 or f. Okay, then what is L alpha of that quantity? L alpha of f is same as L alpha of f1, because f and f1 are same. Then this will be f1 times alpha. What is f1 times alpha? F1 times alpha is same as f1 times alpha 1. F1 of alpha 1, this is not times f1 of alpha 1. What is f1 of alpha 1? F1 of alpha 1 is 1. Then this is equal to 1. This shows that there exists at least one element whose image is non-zero, okay, which is non-zero. Therefore, this L alpha is itself a non-zero function. Okay, this L alpha is in fact a function from this V star to F. Then there should exist an element in V star whose image is non-zero. Therefore, the function itself, the L alpha function itself, is a non-zero function. Then whenever alpha not equal to 0, then L alpha not equal to 0. So or you can consider this as L alpha equal to 0. L alpha is not equal to 0. L alpha is a function from V star, V to V double star, because since L alpha is linear, since this linearity is here, then you can easily write whenever alpha 1 equal to alpha 2, then this would imply that alpha 1 minus alpha. Before that, we consider before we can conclude that the meaning of this statement is the contrapositive of the statement is L alpha equal to 0 implies alpha equal to 0. Now we will prove the reverse implication as well. Whenever alpha equal to 0, L alpha equal to 0. That is very trivial. Whenever alpha equal to 0, you can say that f alpha equal to 0 for all f. Okay, that implies what is f of alpha, that is L alpha of f equal to 0 for all f. Okay, this shows that L alpha equals 0. That means L alpha is a 0 function. Then whenever alpha equal to 0, we can get L alpha equal to 0. So from this you can say and from this argument you can say that L alpha equal to 0 implies alpha equal to 0. From these two statements together, we can consider the statement where alpha equal to 0 if and only if alpha equal to 0 if and only if L alpha equal to 0. Okay, and when you identify this equation, L alpha equal to alpha equal to 0 implies L alpha equal to 0. So this would enable us to verify that this L alpha is a function. Okay, so whenever this alpha 1, I'll write it here. Whenever alpha 1 equal to alpha 2, then you can get alpha 1 minus alpha 2 is equal to 0. Okay, then if you apply this, whenever this holds, we can write this L alpha 1 minus alpha 2 equal to 0. Okay, from this you can write L alpha 1 equal to this L alpha 1 minus alpha 2 is same as L alpha 1 minus L alpha 2. So we will prove it right now, and you can get this is equal to 0 implies L alpha 1 equal to L alpha 2. Okay, so whenever alpha 1 equal to alpha 2, then you can get L alpha 1 equal to L alpha 2. So this is the definition of a function, and immediately we will prove this identity. Whenever L alpha 1 minus L alpha 1 minus alpha 2 is equal to 0 implies L alpha 1 minus L alpha 2. Okay, so now we can consider this L alpha is a function from V to V double star, which is a 1-1 function using this argument. This psi is a function from V to V double star, and psi is a 1-1 function itself. Okay, now consider the psi again. So this is a function from V to V double star, the double dual of V. This is the double dual of V, Now we can get whenever alpha equal to beta implies alpha minus beta equal to 0 implies uh, this L of alpha minus beta equal to 0. Okay, whenever you consider L alpha minus beta, then L, what is L alpha minus beta of f? This is equal to L alpha minus L alpha minus beta of f is equal to f of alpha minus beta, and f is an element of v star. So this f is a linear functional. So you write this f of alpha minus beta as f of alpha minus f of beta, and you write this f alpha minus f beta as L alpha of f minus L beta of f. Okay, so you can get, this is a function anyway, and this can be written as L alpha minus L beta of f. Okay, this is true for all f belongs to v star. So this shows that this function and this function are equal. That means L alpha minus beta equal to L alpha minus L beta. So this is an interesting identity about this L alpha. Now you write this L alpha minus beta is equal to this implies L alpha minus L beta equal to 0 implies L alpha equal to L beta. What is L alpha? L alpha is psi. The definition of psi is psi of alpha is equal to L alpha. Then this L alpha can be written as psi of alpha, and L beta can be written as psi of beta. So this is psi alpha minus psi alpha equal to psi beta. Okay. So whenever alpha equal to beta, you can get psi alpha equal to psi beta. This shows that psi is a function, and we have already seen that psi of what is psi of the c times f plus c times alpha plus c times alpha plus beta. Okay, by definition, this is L of c times alpha plus beta. Okay, you write this is L c alpha plus L beta. Okay, but what is L c alpha? L c alpha of f. By definition, this is f of c alpha, that is equal to c times f alpha, and you write this c times f alpha as this L alpha of f. Okay, so you write this L c alpha of f is equal to c times L alpha of f. Okay, right. So using this identity, if this is plus, then you can get the same identity. This is, if this is plus or minus, if we have plus here, this is plus or minus, then there will be plus here, and there will be plus again here, and there will be plus, and there will be plus. So this is true for any sign, plus or minus. Then this is equal to this implies L c alpha equal to c times L alpha. Using this identity, you can write this L c alpha plus beta as, first you write L c alpha plus L beta, and again you write this L c alpha as c times L alpha plus L beta. Consequently, this is c times psi alpha, that is L alpha, plus psi beta. So this shows that the psi is a linear transformation from V to V double star. Okay, but L alpha equal to 0 implies alpha equal to 0 using the previous identity. So this implies this is equivalent to psi alpha equal to 0 implies alpha equal to 0. Okay, what is the meaning of this? Psi is 1-to-1 map. This is 1-to-1. Therefore, psi is 1-to-1, and it's a linear transformation from a vector space of same dimension V to a vector space of dimension n to the vector space of the same dimension n, because the dimension of V is same as dimension of V star, and dimension of V star is same as dimension of V double star. Therefore, dimension of V and dimension of V double star are the same. Therefore, this is a map from V to V double star. Then the map is 1 1, then if and only if it is onto. Since using the rank nullity theorem, you can easily verify that the map is 1 1 if and only if ontoness. So psi is a 1 1 onto linear transformation from V to V double star. Okay, this shows that V and V double star can be identified using this map. That means using the mapping alpha goes to alpha. So this is a nice identification of the vector space V and vector space V double star. Okay, so this is defined as the next theorem. This is the theorem 17. In theorem 17, it has been stated that let V be a finite dimensional vector space over the field F. For each vector alpha in V, define a map. L alpha of F is equal to F alpha. You can easily verify that this map, this L alpha of F is equal to F alpha. We have already discussed what is the properties of this map, and if you define this L alpha of F, then alpha goes to L alpha is an isomorphism from V to V double star. Okay, so this is the theorem 17. That is what you have proved here. Now we have two interesting corollaries for the theorem. That is, V be a finite dimensional vector space over the field F. Each basis V star is the dual basis for V. Okay, so this is one corollary, and the immediate corollary is let V be a finite dimensional vector space over the field F if L is a linear functional on the dual space V star of V. Then there is a unique vector alpha in V such that L alpha is equal to F alpha. Okay, that means if you start with the finite dimensional vector space, L is a linear functional, then L is a linear functional on V. That means L is a member of V double star. Then there exists a unique vector in alpha. Okay, such that L alpha is equal to F alpha. So this is very trivial because we have already seen that if we have a vector space V and V double star here, this is V and this is our V double star, and we have shown that there exists a linear map from V to V double star say psi and defined to be each alpha is mapped to L alpha. So we will show that means V and V double star are V is isomorphic to V double star. And now we will prove that if you take any alpha here, we start with an element alpha from V double star, you can easily find a unique alpha here. Okay, unique member alpha here such that this L alpha of F is equal to F alpha. Okay, so this is very trivial because the psi is onto. Since psi is onto, L belongs to V double star. There exists for L belongs to V double star. There is a unique this uniqueness is obtained by the 1 1ness. Okay, the map is also 1 1. So the unique alpha belongs to V such that this psi of alpha equal to L alpha. So this is the definition of ontoness. So the uniqueness comes from the 1 1ness. Okay, what is the meaning of this? Psi alpha is equal to L alpha. So what is psi? Then how will you interpret this? Okay, so this is this implies such that this psi alpha is equal to not L alpha, that is equal to L, because that means every L there exists a pre-image. That means for every L belongs to V double star, there exists a unique alpha such that psi alpha is equal to L. Okay, so this implies, what is psi alpha? Psi alpha is equal to L alpha. What is L alpha? L alpha is equal to L. Okay, so for any alpha belongs to for any L belongs to V double star, there exists unique alpha satisfying this condition. Okay, these are elements of V double star. Okay, these are elements of V double star, and or you can consider L alpha and L are a function from functions from V star to F. So this is true for L alpha of F equal to L of F for all alpha belongs to V star, because these functions are from V star to F. So in order to get the equality of two functions, that should be coincided with every points of the domain. So the domain is V star, so this L alpha is equal to L alpha of F is equal to L of alpha. So this implies, by definition, L alpha of F is equal to F of alpha, and this LHS is L of F. Okay, for all F belongs to V star. So this is the first corollary. Corresponding to each L belongs to V double star, there exists an element alpha in V such that L alpha is equal to F of alpha for all F belongs to V. In fact, this L alpha is same as L of F is same as L alpha of F. Okay, so this is a trivial identification. Now we can discuss the next corollary. Next corollary is how to find, if we start with a dual basis or start with the basis of dual space V star, say F1, F2, etc. Fn. The question is, can you find a basis of V? Okay, we have two vector spaces here, V, and this is V, and this is V star. Okay, this is not V double star, this is V star. So what is the question here? If you choose a basis here, F1, F2, etc. Fn. Okay, so can you find, corresponding to the basis, can you find a basis of V, say alpha 1, alpha 2, etc. alpha n, such that this Fi's are the dual basis of this alpha 1, alpha 2, alpha n? That is the question of the next corollary. Let V be a finite dimensional vector space over the field F. Each basis for V star is the dual basis for V. Okay, so every basis for V star can be considered as a dual basis of some basis of V. So this is next question. So for this we use the same isomorphism, psi from V to V double star. For this we have to consider three vector spaces. One is V, and second is V star, and third one is V double star. Okay, I'll consider V double star here. So this is our V, and this is V star, and this is V double star. I represent elements of V as alpha, and elements of V star as F, and elements of V double star as L. Okay, now we start a basis, say V or V star, say, or we can consider a basis V star consisting of the basis elements F1, etc. Fn. So this is in fact a basis, need not be a dual basis for some. We need to prove that this is a dual basis of something. So we start with the basis of V star, then you can construct the dual basis for V star, that is V double star, that consists of vectors L1, L2, etc. Ln, such that Li of Fj equal to delta Ij. This is the definition of dual basis of V star. Okay, so if we start with the basis here V star, then you can construct a basis V double star here. Okay, so there is a correspondence from V star to V double star. But we know that if we have the elements L1, L2, etc. Ln, then we have shown that each L belongs to, from the corollary 1, we can get each L belongs to V star, V double star, there exists an element alpha with this property. So corresponding to this L1, you can find an alpha 1 such that L1 alpha 1 equal to f of alright L1 of f1 is equal to, or L1 of f is equal to alpha f of alpha 1 for all alpha. Okay, so for all f. Similarly, corresponding to L2, you can get alpha 2 such that L2 of f is equal to f of alpha 2 for all f belongs to. Okay, the similar way you can construct an element alpha n such that Ln of f is equal to f of alpha n for all f. Okay, so this is the first corollary. Now we can define a new set of elements in V, say alpha 1, alpha 2, etc., alpha n. How do you obtain these elements? These elements are obtained by this relation, okay, or obtained by first corollary, or obtained by taking the inverse images of L1, L2, Ln corresponding to the map psi. Okay, that means if we have we can easily define a psi from V to this is our psi. Then if you choose L1, L2, L3, etc., Ln, you can easily find out elements alpha 1, alpha 2, alpha 3, etc., alpha n, such that psi of alpha 1 is equal to, what is the translation of these statements? Okay, this shows that L1 of f is equal to f of alpha 1. That means what is L1 of f, or you write this as this is L1 as L alpha 1. Okay, and similarly you can consider this corresponding to this this alpha and alpha 2 alpha n are obtained by taking the pre-images of L1 under the psi. Okay, so the psi of alpha 1 is L1. Okay, in fact psi of alpha is Li. This is the definition. Okay, what is psi of alpha? That is L alpha I, that is equal to Li. So this is obtained from this is true for all f. That means L alpha I of f is equal to Li of f. So this is what we have written here. L alpha I of f is equal to f of alpha. Okay, so this is L1 of f is equal to f of alpha I for all I. So these are the pre-images of L1, L2, Ln with this psi. This psi is an isomorphism. So inverse, psi inverse is also an isomorphism. Psi inverse is also an isomorphism. So alpha and alpha to alpha. So psi inverse is isomorphism is psi inverse is 1, 1 or non-singular. But non-singular maps carries independent set to independent set. Okay. So since this L1, L2, etc., Ln are linearly independent implies this alpha 1, etc., alpha n are linearly independent, because psi inverse is one non-singular map. Therefore, so now every non-singular map carries a linearly independent set to linearly independent set. So this is a linearly independent set of V. So this form a basis. Okay, so this is a basis for B. So corresponding to each B star, we can construct B double star. From that you can construct a basis. B is consisting of vectors alpha 1, etc., alpha n. Then what is the relation between these two? That it remains to observe these the relation between these two. We have already established what is the relation between Li and alpha I. Now we will establish the relation between Fi and alpha I. Okay, so how will you find Fi of alpha j? What is Fi of alpha j? Fi of alpha j is equal to, by this definition, Fi of alpha j is equal to Li of alpha j, because L1 of f is equal to f of alpha 1 for every f. So if you replace this Fi, so you can get L1 of Fi is equal to Fi of alpha 1. Similarly, Fi of alpha 2, etc., Fi of alpha. That means this is Fi of alpha j, that is equal to Li of alpha j, but Li of alpha j is equal to this is nothing but delta ij. Okay, now this can be written as this is fj not alpha j. Li of fj, that is equal to fi of alpha j, that is equal to delta j. So fi of alpha j can be obtained from this relation. Clear? F if you write this is if you replace this f by fi, then you can get L2 of fi is equal to fi of alpha 2. Similarly, this is true for L1, L2, L3 for all numbers. Then this can be written as Li of alpha is equal to Lj, or I'll write this is Fj. This is true for uh, you can replace one suffix by I and another by j. Then Li of alpha Fj is equal to this is F, and these two suffixes are the same. So you write it as Lj here. Lj Fi is equal to Fi alpha j. Okay. Now you can write Fi alpha j, that is Fi alpha j equal to Lj. This is Lj f of I, Fi. Okay. Lj Fi. From this you can say that Lj Fi is delta ji. So this is delta ji. That is same as delta ij. Delta j and delta ij are same. So you can get for every basis of dual space V star, there there would exist a basis of V, say B, such that this B star is the dual basis for B. Okay, so this proves corollary. The next corollary is the second corollary of theorem 70.